Before working with series parallel AC circuits, make sure you recall how to work with complex numbers. Complex numbers we use as phasors to describe our voltage and current, and that is going to allow us to do some calculations with Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law. So make sure you understand how to work with complex numbers in both rectangular format. Remember, that is the x plus yj form of a complex number, and of course polar form as well, where we have a magnitude and a phase angle. Okay, so make sure you understand these two formats, how to convert between them, and how to add and subtract and multiply and divide with complex numbers. It's also helpful if you remember how to use your calculator for this, so either use previous videos that I've created or find information in your manual for your calculator, and make sure you practice that before you start practicing these problems. It'll be much easier. Also, remember all of your rules for series parallel circuits for DC. So if you need to review the concepts there, this is chapter 7 in your textbook. You might want to go review some problems in DC first, because AC is really the same thing except that we're using phasors. Okay, so let's work through a problem. Again, we'll do the reduce and return method with this, but there's really not much reducing to do here. What we want to do is start reducing until we get to one impedance for the entire circuit. So let's just start right here with our resistor and capacitor. Those are in parallel. So, and I'm going to call that impedance. I'm going to call that ZA right here. So to find ZA, we have R2 in parallel with X sub C. So let's calculate that. So remember, that's going to be 1 over R2 plus 1 over negative XC times J. Okay, those are the impedances. So another way to do this, if you have two parallel branches, okay, and these parallel lines represent parallel. You have two parallel branches. We could also do what we call product over the sums to calculate the total, which would be ZR times ZC over ZR plus ZC. So I'm also going to show that here. So 2 ohms, and that's at 0 degrees. So I'm going to leave off the 0 there, times a negative 8J, I'm putting that in parentheses, over 2 plus negative 8J, or minus 8J. Okay, so once we calculate that, your answer, you can give that in rectangular coordinates or polar coordinates. It really doesn't matter if you're using your calculator. So we've got 1.94 at negative 14 degrees. That's polar form, or 1.88 minus 0.47 times J in rectangular form. And that's the impedance of block A right here. All right, so this block impedance we would just add to the impedance for R1, add to the impedance of L to get our total impedance of our circuit. Okay, so it doesn't matter if you're using your polar form or your rectangular form if you're using your calculator. Either is fine. If you're doing this by hand, you're going to want to use the ZA that is in rectangular form because that's a little easier to add and subtract. And then I'm going to add my ZR1, which is 3 at 0 degrees, so I can leave off the 0 there. And ZL would be 6 at 90 degrees, or 6J if you're looking at this in rectangular form. So ZT in this case, I'm going to go down here. ZT is in rectangular form 4.88 plus 5.53 times J, or in polar form 7.38 at an angle of 48.56 degrees. Again, you don't have to get both. You can just stick with one or the other. I'm just wanting to show you both in case you're working this out with me, so you'll see that you have the right answer no matter which form you're selecting to use. I'm going to try to give you both, at least for right now. Now, we do that because we want to find our source current, and source current is always E over the total impedance of our circuit. Same thing for DC, except in DC we were talking about total resistance, and in AC we're talking about total impedance. So you need the phasor form for the voltage here, and we have that. It's given to us as 30 volts at 0 degrees. And I'm going to use the polar form of our source current. Of our total impedance, 7.38 at an angle of 48.56 degrees. If you're doing this by hand, it's just 30 divided by 7.38 to get your source current, which should be about 4.07. And then the angle would be 0 minus 48.56. And that gives you a negative 48.56 degrees. At this point, we can find our voltage drops. So VR1 would be I sub S times ZR1. We could say R1, but let's stick to the impedance notation here. So 4.07 negative 48.56 degrees times, remember 3 at 0 degrees, I could leave out the 3. But VR1 should be about 12.2 volts. And the angle, of course, negative 48.56 degrees. Let's find the voltage drop across our inductor. Also, that's still the source current through there, so that's going to be I sub S times ZL. So our 4.07 negative 48.56 degrees. And we have a 6J, or in polar form that would be 6 at 90 degrees. So V sub L should be 24.39, and the angle would be 41.44. Now I'm going to find the voltage drop across A. That's the portion of the circuit that has my R2 and my capacitor in parallel. So I'm going to take the source current and multiply by ZA, because when I combine these, when I combine this portion of my circuit, it basically turns into a single component. So the current through that combined impedance would be I sub S. So 4.07 negative 48.56 degrees. And that, remember, up here, ZA, I'm going to use the polar form, 1.94 at an angle of negative 14 degrees. So we should have 7.89 at an angle of of negative 62.56 degrees. So that's VA. Now remember, we got ZA by combining two parallel impedances. The parallel impedances are going to have the same voltage. So the voltage drop across R2 is VA. The voltage drop across C here, or the capacitor, is also VA. So if I want to find the portion of our source current that will be seen through R2, I would just take VA, which is VR2, and divide by 2 at 0 degrees. So that's 7.89 at negative 62.56 divided by 2 at 0 degrees means I have about 3.95 amperes at negative 62.56 degrees. And for our capacitor current, it's the same voltage because it's in parallel with that resistor. And this time I'm dividing by 8 at negative 90 degrees. That's the capacitor impedance. So 7.89 at a negative 62.56 degrees. 8 at negative 90 degrees. So that means I've got just under 1 ampere at an angle of 27.44 degrees. Now, if you wanted to check your work, remember that VR1 plus VL plus VA should equal your source voltage. And remember that IR2 plus IC should equal I sub S. Okay, so if you want to plug those into your calculator, you can check them. In DC, it was pretty easy to see that those added up because the numbers just added up. It was easy to see. In these polar coordinates, it's a lot more difficult to see that they add up because of those angles. But you can plug this into your calculator and see that these indeed are true. They might be off by a little bit because we're doing a lot of rounding in our calculations here. But go back over that and practice this problem, and I'll work a few more for you in